Welcome back to the second video for Thursday, January 14th. The purpose of this video is to review the instructions for Lab 1, which is the lab that we're going to do next Tuesday. So by reviewing it today, hopefully we'll know what we're doing when we actually do it next Tuesday. The purpose of Lab 1 is to make some calculations about the density, which is an intrinsic property, of selected materials, and potentially make some connections to another intrinsic property of materials, which is the ultimate tensile strength. And we haven't talked about that yet, but we will soon enough. All right, so here's what we've got. We've got a couple different materials. We've got some different chunks of wood. This is not actually one of the chunks of wood that we're going to use for Lab 1, but it's close enough, and it's what I had in my office. So this is symbolic of a chunk of wood that we're going to measure the density of. We've also got some plastic specimens, all of which are in the shape of a dog bone like this, which are made using the injection molding machine. And we've got some metal specimens that are shaped kind of like this. So it's part of a metal dog bone that has been tensile tested and pulled apart. All right, so the density of material is equal to the mass of that specimen divided by the volume of that specimen. So when you're taking the calculations of a chunk of material like this, a prismatic type chunk of material, it's fairly easy to calculate the density. All you have to do is, first of all, measure the mass, which is pretty easy. We can use a scale of some sort, a triple beam balance or an electronic scale. We have both, so we can measure the mass of the object. And then we need to divide by the volume. And an object like this is pretty easy to calculate the volume because all you have to do is measure the length and measure the width and measure the height and multiply them all together and you've got the volume. So then you take the mass divided by the volume and voila, you've got the density of the material. What's not quite so easy to think about though is how do you calculate the volume of this, or how to calculate the volume of this? Well, there is a pretty clever way to do that we're going to use in Lab 1, and that is by measuring the displacement of these objects when we dunk them in a graduated cylinder full of water. So that's the method we're actually going to use. So with that, I'm going to switch over to the document cam, and we're going to talk through Lab 1. So I would recommend that you flip in your lab manual to page 7 now so that we can talk through Lab 1 together. All right, here is Lab 1. It starts on page 7. And before we start reviewing the lab, let's go ahead and review some items of terminology. We know that the density of a material is equal to the mass of that material divided by the volume. Notice that mass and volume are actually both extrinsic properties because the mass of something depends on how much of that something you have. And the volume also depends on how much of that you have. So even though these are both extrinsic properties, when you divide the mass by the volume, you have density, which is an intrinsic property. It doesn't really matter if I'm measuring the mass and the volume of some small specimen of steel or some large chunk of steel. I should get the same density regardless of how much of it I have. So that makes density an intrinsic property. With regards to mass and volume, we could choose the units that we're going to use. We could measure this in kilograms per meter cubed or grams per centimeter cubed, or a bunch of other different units, but we're going to use what I sometimes call freedom units in this lab. And so we're going to use pounds mass for the mass, and we're going to use inches cubed for the volume. So we're going to measure density in pounds mass per inches cubed, or per cubic inch. All right. But this actually is a good time to discuss the ambiguity surrounding the term pound. All right, and you notice that I've written LB, that's the abbreviation for pound, and I've crossed it out because I want you to be really careful in this class, and actually I don't want you to use this unit. LB is not really a valid unit at all. You have to be careful when you're using the quote-unquote pound. You're actually referring either to pounds force or to pounds mass, but they're two different things. One is a mass and one is a force. Remember, mass, you probably learned this in high school science, mass is the amount of matter. It's the amount of stuff in a specimen. That's the mass. The force is related to like a push or a pull. that is exerted on that specimen. So these are not the same thing. Normally, people are really lax about this, and there's a good reason why. It's sometimes okay to be lax about this that I'll talk about in a second. But normally when people are talking about pounds, what they really mean is pounds force, because they step on a scale in their bathroom or something like that, and that tells you how much force your body is exerting on that scale, or how much the earth is pulling on your body downward towards the center of earth, right? So that scale is measuring pounds force. The equivalent metric unit is newtons. Newtons is a unit of force in the metric system. So you can directly convert, that's what I have this symbol there for. You can directly convert, there is a conversion factor between pounds force and newtons. All right, so there's a direct conversion directly between pounds force and newtons. They're both units of force, so you can convert between them. All right, on the other hand, pounds mass is a unit of mass. It's how much matter is in an object. And kilograms is also a unit of mass in the metric system. So we can convert directly between these. As I recall, it's 2.2 pounds mass per kilogram. So you can directly convert between pounds mass and kilograms, all right? But the reason I say these are not equal, in general, a pound force is not the same thing as a pound mass. The only time when we're kind of lucky that a pound mass exerts a force of 1 pound force is, by definition, on the surface of Earth. All right, so if we're on the surface of Earth, which we happen to be right now, then it's true that 1 pound mass exerts a force of 1 pound force. All right, so then you can kind of say they're equal, at least numerically. The number will be equal. They're not the same thing. A pound of mass is not the same thing as a pound force because one's a mass and one's a force. But you can set them equal to each other numerically as long as we're on the surface of Earth. All right, so does that kind of clear things up? I hope it does. Pounds force can be directly converted to newtons. Pounds mass can be directly converted to kilograms, or vice versa. And if we're on the surface of Earth, then 1 pound mass exerts a force of 1 pound force, and 20 pounds mass exerts a force of 20 pounds force. All right, so you can directly convert these easily if we're on the surface of Earth, but that would not be true if we're on the moon or on Jupiter or on Pluto or something else like that. So how does this relate to our course in TEC 293? Well, first of all, you can cross out LB because LB is not specific enough. So I should never see the units LB in one of your lab reports in any part of this class. LB is not really a valid unit because we can always be more specific and we can say, is it a pound force that we're referring to or is it a pound mass? All right. In lab 1, this is one of the only labs in this class where we actually are dealing with mass. So we actually are going to have pounds mass in lab 1. Most of the time, in almost all of the other labs in TEC 293, we're going to be dealing with forces. For example, the amount of force that we apply to this to pull it apart, or to compress it together, or to bend it, and to cause deformation. So most of the time in this class, we actually are going to talk about pounds force. But in this particular lab, in lab 1, we are actually dealing with pounds mass. All right, let me know if you have any questions about that. It's just a little bit ambiguous. I think it's actually more confusing because as English speakers, we use the same base unit, pounds, for both force and mass. If we were not native English speakers, then we would just grow up recognizing that forces are measured in newtons and masses are measured in kilograms. It's kind of a relic of the English language or the English system that this becomes confusing because we have pounds force and we have pounds mass, but they're not the same thing. Only on the surface of Earth are they quantitatively, the numbers, numerically, equal to each other. Okay, I think that's enough about that for right now. Let me know if you have questions about that. All right, so we talked about the objective before. we're going to need to use a scale to measure the mass and some type of ruler to measure the dimensions of the specimens. We're going to need to use a graduated cylinder and some water to measure the displacement of some of the irregularly shaped specimens like this one. We're going to need a thin wire because that's what we're going to use to hold on to the specimen as we dunk it in the graduated cylinder. We need safety glasses. Yeah, it's a little ridiculous to wear safety glasses in Lab 1. All we're really using are some blocks of wood and metal and plastic and rulers and stuff. But it gets us in the habit, and it's a professional practice of wearing safety glasses. So we're going to wear safety glasses. And then here's our specimens. We've got 3 different metal specimens, steel, aluminum, and copper of a couple different types. We've got 3 different kinds of plastics, ABS, polypropylene, HDPE, and we got 5 different kinds of woods. So I have 5 blocks of woods down there in the lab: oak, mahogany, walnut, white pine, and hickory. All right, so for each of these specimens, we're going to need to measure the mass as well as the volume. So let's actually skip to part B first, because that's simpler. Okay, part B explains how we're going to do this testing for the wood blocks. So for all of the blocks of wood, and actually we're going to include the HDPE in here as well, because the HDPE is one plastic where I actually do have a big solid chunk of HDPE. The other plastics are in a dog bone specimen like this, but the HDPE is in a prismatic rectangular block like this. So for all the woods and HDPE, we're going to follow this procedure. We're going to find the mass by using a scale, and we're going to record the mass in grams, and then we're going to convert to pounds mass. You know that you can do this conversion because you know that 2.2 pounds mass is equal to 1 kilogram. So first you'll have to convert from grams to kilograms, and then convert kilograms to pounds mass. And then we're going to record the dimensions of the wood specimen using the ruler. So I'm going to measure those in the video on next Tuesday, and then you're going to record those on your data sheet. And then using those dimensions, you can calculate the volume in inches cubed using this formula. And now that you know the mass and the volume, you can calculate the density in pounds mass per cubic inch. And you can kind of do a little, I guess, kind of dummy check here. You know that the density of wood should be less than the density of water. Why? Because wood floats. Almost all kinds of woods float. I think there are a couple kinds of wood that actually don't float, but the vast majority of woods will float. And the density of water is, I know it's 1 gram per centimeter cubed. You can do that conversion to pounds mass per inch cubed, but you should find that the density of all these different wood specimens should be a little bit less than the density of water. Okay, so that's how we find the density of all the wood specimens and the HDPE. Now I'm going to go back to part A. Part A is where we're going to find the density of the rest of the plastic specimens and all of the metal specimens. So what we're going to have to do here, because these are irregularly shaped, I can't use a ruler and find the volume just by measuring some simple dimensions like the length, width, and height. So what we're going to do is use the displacement of a graduated cylinder of water when I dunk those specimens into the graduated cylinder. So here's what we're going to do. First, you got to find the mass. So we'll measure the mass of these specimens on a scale. And we're going to record the mass in grams. And then you can convert the mass in grams to pounds mass. And then we're going to find the volume. So we're going to fill the graduated cylinder up to about, it doesn't really matter if this is exact, but somewhere about 70 milliliters. And then we are going to record the initial water level. And then we're going to take a wire and we're going to wrap that wire around the specimen so that we can kind of hold on to it as we're dunking it in there. And then we are going to dunk this into the graduated cylinder, and then we will record the new reading for the water level on the graduated cylinder after we've submerged that specimen. So then we've got 2 readings. We got the before and after reading, and we can subtract those 2 to find the water displaced by the specimen, and then the displacement is going to tell us the volume. So we can convert the milliliters of water displaced to cubic centimeters. That's easy because 1 milliliter conveniently is equal to 1 cubic centimeter. Isn't the metric system convenient? Sometimes it really is. So then we can get the volume in cubic centimeters, and we can convert the volume in cubic centimeters to the volume in cubic inches by using this conversion factor. And now we have the mass from step 2, and we have the volume in inches cubed from step 9. So now you can do the conversion and calculate the density in pounds mass per inch cubed. All right, so that's how we can do it for both the wood specimens, the block type specimens, as well as the irregularly shaped specimens. So that's all of part A. And then in part C, I want you to use this data to make some connections to other intrinsic material properties. So what I want you to do is go to this online material reference webpage called matweb.com. It's not named after me, unfortunately. MAT stands for materials, so it's kind of short for materialsweb.com. But you're going to use this website quite a few times in this class. It's a really convenient website that lists the material properties of lots of different, hundreds, maybe thousands of different kinds of materials. And what I want you to look up here for lab 1, I want you to look up the ultimate tensile strength of each of these specimens. And this brings up a point. If you look on matweb.com, you might find that, maybe for, say, what specimens do we got? Oak. If you look up oak on matweb.com, there are probably going to be a whole bunch of different kinds of oak that you can look up. So I'm trying to be as specific as I possibly can here. If you look up American red oak, there's probably only one listing on matweb.com for American red oak. If there's more than one, then just pick one. They should be very, very, very close. If there's multiple kinds of American red oak, then those data points are probably very, very similar. So just pick one. So go to matweb.com, find the ultimate tensile strength, and it might have it in several different units. Look for the one that is in PSI, pounds per square inch. All right, we haven't really talked about ultimate tensile strength yet, but we will in this class. What it is basically how much stress this material can withstand before it fails. It's the maximum amount of stress that the material can handle before it fails. While you're there, you're going to use this website a lot in this class. So while you're there, go ahead and just look at what else MatWeb has, what other data points it has. All right, then we get to the results section. What I want you to do is make a table. Don't forget to label it Table 1 in your lab report. In the table, make sure you show all of your experimentally obtained results. So there's not that many raw data points in this lab. So go ahead and show all of the lengths and the widths and the heights for some of the block specimens. And go ahead and show in this table, or in a separate table, show the different displacements, the initial displacement and the final displacement. Show how you calculated the masses and the volumes and the densities for each of these different materials. If you'd prefer, I'll also, what this says, I don't know if you can read this or not, but what it says here in red ink, this can also be on a handwritten page. If that's more convenient for you, that's fine. Just make sure it's neat and clear and I can follow what you've written. So if you want to put that on a handwritten page, that's fine. Just make sure you refer to it in your lab report. Okay, then make another table. And in that table, I want you to show the density of each material and the ultimate tensile strength in each material. Make sure you label these with units. So the density we're calculating in pounds mass per cubic inch, and ultimate tensile strength should be in PSI. So make sure you include the units, not just for all your plots and graphs, but also in your tables. And then I want you to make a plot. So this should be a scatter plot. It should look kind of like this. I don't know if you can see it, but there's a bunch of data points, just like dots. They're just data points because they're plotting the density in pounds mass per cubic inch on the horizontal axis and the ultimate tensile strength in PSI, pounds per square inch, on the vertical axis. Make sure anytime you have a graph like this, you have a title. Make sure you have a description or a label on the horizontal axis as well as units. And make sure on the vertical axis you also have a label as well as units for the vertical axis as well. All right, so that should look like. The only other thing that should have here under the figure, you should have figure 1 and then describe it, scatter plot of density versus ultimate tensile strength or something like that. Just describe what this plot is. Okay, and then in the discussion, there's just a couple of discussion questions. First of all, does there appear to be a correlation between the density of the material and its ultimate tensile strength? For example, in general, if you increase the density of a material, does it seem like you also get higher ultimate tensile strength? Make some educated guesses just by looking at this plot. All right. You could also break it down to different types of materials. So you might possibly say, well, it's hard to determine on this plot if there is a connection between density and ultimate tensile strength. But if I look at, say, just the wood specimens, maybe for among the wood specimens, maybe as I increase the density, the ultimate tensile strength increases. Or maybe for just the metal specimens, we had copper, aluminum, and steel, maybe as I increase the density, the ultimate tensile strength increases. So look at the individual categories of materials as well as the overall picture. Okay, and use some specific examples from this experiment. And then number 3 are where I want you to give some examples. So if you're in charge of designing some piece of equipment, something, when might you want to use a material with a high density? So when do you want to use something that is dense? And if you want to, you can use this connection. If there is a connection between high density and high ultimate tensile strength, you can use that. And you could say, well, I know that in general, if I have a high density, you usually have a high ultimate tensile strength. And for this particular piece of equipment, I want a high ultimate tensile strength. So I want to use something that has a high density. All right, you can make connections like that. Number 3 is the last one, and it's just the opposite. And it says, if you're designing something, when might you want to use something with a low density? When might that be a good option? For both these, give at least 2 specific examples. Looking at the schedule that I keep at the front of my lab manual, I can see that Lab 1 is due on January 26th. Remember, everything is due at 11:55 p.m. So make sure you write your lab report, save it as a PDF, please, if you can. It just makes it easier if they're consistent for me. And upload it to RegNet under the Assignments tab. There should be an assignment called Lab 1. And upload it under that tab in RegNet by 11:55 p.m. on January 26th. All right, that's about it for the description of Lab 1. It's a pretty straightforward lab. There's not a whole lot to it, but if you have any questions about it, by all means, let me know. I'd be happy to clear up any potential confusion about Lab 1. All right, so that's going to be about it for today. Let me know if you have any questions. Have a great weekend, and I'll see you next time.